Welcome to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, let us briefly recap what we did in the previous lecture. So, in the previous lecture we talked about the microscopic details of treatment of ionic and electronic polarizability, in which we saw that the polarizability, there is a when you estimate the polarizability and when you plot the dielectric constant shows a sort of resonance at a frequency omega, and this is the difference that you create. So, if this is 1, this would be epsilon r electronic and this would be omega O E, for instance, and at the same time you will have a peak in epsilon r double prime. So, this is epsilon r double prime at the, so this is where your omega tau will be equal to 1. So, this is what we saw, and we also started with a simple model for our dipolar relaxation or dipolar polarizability, where we said that we are going to treat. So, for dipolar polarizability polarization, we started with the bistable model, where we assume that you have a molecule, let us say like this, okay, and this molecule, so it is connected in this fashion, and this molecule transverses to another position which is like this, let us say. So, this atom is basically moving to this position from position 1 to position 2. So, you might consider this as a rotation of, let us say, a molecule. So, this could be a different atom altogether. So, basically what is happening is that if you plot the energy landscape, the molecule is shifting from one stable position to another stable position. So, this is position 1, this is position 2, and it has to overcome an energy barrier EA or QA, let us say. So, this is energy and this is, let us say, distance or position. So, it goes from one position to another position and this happens by hopping. And when the dipolar relaxation happens, basically when you plot polarization as a function of time, the evolution of electronic plus ionic component is almost instantaneous, because it happens at a frequency which is below 10 to the power 11 hertz. So, basically time scale is of the order of 10 to the minus 11 second, and this happened extremely fast. So, your electronic and ionic polarization develops almost instantaneously, and then dipolar polarization develops slowly until it saturates and reaches a polarization called as saturation polarization, that is PS. And at any given point of time, this is represented by PdT, the time dependent dipolar polarization, and this is what is dependent upon a model that we will discuss. So, let us say we were talking about the probabilities of jump. So, when you have 0 electric field, then probability of jump from 1 to 2 will be equal to A exponential some, let us say, f naught, okay, f naught into exponential of minus QA divided by KT, okay, and this is basically energy barrier, it being a Arrhenius process, and this is the thermal energy KBT. So, you might have similar and so for 1 to 2 this is the frequency. Similarly, for 2 to 1 the jump probability will be f naught exponential of minus QA by KT, and these will be sort of equivalent at equilibrium. So, when there is no field, then F12 will be equal to F21, right. So, there are equal energy barriers from both sides as a result. So, and when you apply a field, upon application of a field E, the potential energy of two sides changes. So, this changes the and this is, let us say, delta Q amount. Okay. So, what will happen is that this energy barrier on one side will become smaller and another side will become larger. So, let us say this is 1, this is 2. So, on this side you will have reduction from QA minus delta Q, and from this side you will have increase from QA minus plus delta Q. Okay. And this delta Q will basically correspond to basically mu E, right, and mu E is nothing but Q into D into cos theta. So, assuming that cos theta is equal to they are collinear. So, we will basically so mu D Q D E into cos theta. So, essentially we will say that this energy is nothing but mu E for complete alignment. Okay. So, this is the change in the energy when that happens when you apply the electric field. So, assuming that theta is equal to 0 degree. Okay. So, if this is the case, let's build upon further. So, assuming that we have, so first assumption is that we have total number of bistable dipoles are equal to n per unit volume. Okay. And n is a small number, so that dipoles are non-interacting. Okay. So, non-interacting means there are no internal electric fields that set in. And third is we assume that theta is equal to 0 degree. So, when theta is equal to 0 degree, then the extra Q that will be is equal to mu E, okay, such that delta Q is mu E. So, when you apply a field, then F122 will be equal to F naught into exponential of minus of QA minus mu E divided by, you can write KBT. Okay. And similarly, and if you just break it up, this will become exponential of minus QA by KT into exponential of mu E by KBT. This will become basically F. Okay. So, when we have no field, then F was equal to F naught into exponential of minus QA by KT. So, this is F into exponential of mu E by KBT. So, basically it is saying that the site where the energy barrier has lowered, the probability has increased by the amount exponential mu E by KT. So, the flow to one direction has increased, but flow to from other direction will correspondingly decrease. So, similarly, when you talk of F21, F21 will be F into exponential of minus of mu E by KT, right. So, from one side there will be more dipoles moving to another side, whereas from another side there will be lesser number of dipoles moving to the first side because of the increase in energy barrier. So, but however, we say that mu E by KT is sufficiently small, and this is verifiable. You can choose the values of mu is nothing but Q dot D. So, if you put in the some approximate magnitude of mu, Q and D, and then the value of E, then this is smaller than, this turns out to be smaller than 1. So, for all practical purposes mu E by KT is smaller than 1. So, we can approximate exponential of, so if this is x, then we can write exponential of x is equal to 1 plus x plus dot dot dot, and we can approximate it as 1 plus x, okay, for smaller values. So, as a result, we can write F12 will be equal to F into 1 plus mu E by KBT and F21 will be equal to F into 1 minus mu E divided by kBT. Okay. So, this is the approximation that we make. Now, under equilibrium, let us say we have equilibrium conditions. That will mean that average population does not change with time, right? Average population at a given site will not change with time. What will it mean is that, so outflow from 1, that is N1 into F12, N1 is the population at site 1, right? F12 is the probability of jump from 1 to 2. So, this will be the number of dipoles or number of atoms or number of species leaving the site 1. This will be equal to N2 F21 and this will be population at site at 2, whereas F12 and F21 will be the probabilities. So, we can say that this is equal to F into N1 into 1 plus mu E by KT is equal to F into N2 into 1 minus mu E by KT. So, if we now do the mathematics, simple maths here, so N1 minus N2 is equal to minus of N1 plus N2 into mu E by, so I have written KT, just replace this with KBT, okay, this is Boltzmann constant. So, this is first relation, we get N1 minus N2 is equal to minus of N, because N is equal to N1 plus N2 because number of dipoles are conserved. So, capital N into mu E by KBT, okay. So, this is first thing that we get. Second thing, the polarization can be written as PS can be written as change in the number of jumps, that is N2 minus N1, more have reached N2, few have reached N1 because of change in the energy barrier. So, total number which is shifted, change in the dipole density multiplied by change in the number of dipoles per unit volume multiplied by the dipole moment, right. So, this will be equal to basically you can say okay, let's take it as this right now, okay. Now, let us see, so this is the another relation that we have, PS is equal to N2 minus N1 into mu. Now, let us work out what is the time dependence of PDT. So, let us say the first we want to work out what is rate of change of dipoles, let us say on site 1, this is equal to outflow from 1 minus inflow from 2, right. So, basically this is dN1 divided by dt, this is equal to minus of N1 into F12, right, plus N2 into, right. So, this is the rate of change of dipoles on site 1. We also know that N1 plus N2 is equal to N, which is constant. So, if I now differentiate, so this is constant, but N1 and N2 are changing, right. So, dN1 by dt is equal to minus of dN2 by dt, this is fine. So, as a result we can write d of N1 minus N2 divided by dt, this will be equal to 2 of dN1 by dt, or it will be equal to 2 of minus of 2 dN2 by dt. right? So now let's go back to our previous this thing. We are saying that basically we are saying dn1 by d2 is equal to 1 over 2 dn minus n1 minus n2 divided by dt. So essentially we are saying dn1 by dt is equal to 1 over 2 d of n1 minus n2 divided by dt. This was equal to minus of n1 f12 plus n2 f21, right. So this is equal to minus of n1 into f into 1 plus mu e by kbt plus n2 into f into 1 minus mu e by kbt. Okay. So if you now do the just some substitutions here, you will get minus of n1 minus n2 into f minus of n1 plus n2, okay, into mu e by into f into mu e by kbt, all right. Or you can write this as or alternatively I can write this as half of d of n2 minus n1 divided by dt. This is equal to minus of n2 minus n1 f plus n1 plus n2 divided by kbt into f mu e. Okay, I have just changed the minus sign, just multiplied by a minus sign everywhere. Now what is this? This is nothing but 1 over, we said that P is equal to n2 minus n1 into mu. So I replace this, so this becomes 1 over 2 mu into dp over dt. What is this becomes? This becomes minus of P divided by mu into f, plus this becomes n into f. So n into I have changed something here. What is it? Yeah, n into f into mu into e divided by kbt. Okay, so is everything all right? Minus of n. So yeah, so now we can do one more thing. We can bring this f here, dp by dt plus p, this will be equal to n into mu square e divided by kbt, all right. So we can, and 1 over, and f is the jump probability which is in per second, right, frequency. So this 1 over 2f can be approximated now as, so assume, so this 1 over 2f is equal to the relaxation time or time constant, okay. Okay, so we can write this as 1 over tau dp by dt plus p. This is equal to, basically we can say n into mu square e divided by kbt, and if you recall, mu square divided by kbt is nothing but dipolar polarizability, right. So now writing this in terms of polarization, which is time dependent polarization. So among the polarization components, if you see, the time dependent part is the dipolar part, whereas the ionic and electronic parts are nearly time independent, right. So we can replace this P. So since dipolar polarization is time dependent, we can write this as 1 over tau into dpd, and it is a complex quantity, dpd divided by dt plus pd star is equal to n into alpha d into E star, where alpha d is nothing but dipolar polarizability that we derived earlier, right. So, here we say that at 0 frequency, so this is the expression that we get 1 over tau dp by dt plus p is equal to n alpha. So, what is this n alpha e? So, we can see that this is the dipolar polarization, this is time variation of dipolar polarization, which means this should be the net polarization or saturation polarization that we should obtain after sufficiently long times. So, here we define that let us say at 0 frequency I achieve a polarization of PS, right. When the frequency is very small, all the mechanisms are contributing, then what we get is let us say static polarization, okay. That is the maximum I can obtain, right. And then at then I also define then PD is nothing but dipolar polarization. So, if I simplify these steps, so of course to solve this you need to do some simplifications. So, let us say that for ionic and electronic your time scale is faster than this. So, basically time scales are very fast. In fact, I can say time scales are smaller than this actually, okay. So, they are very fast time scales, hence, so for high frequencies I can write a component P infinity, this is equal to Pi plus P electronic, okay. Correspondingly, so for high frequency polarization is this, and I define a dielectric constant as epsilon r infinity. So, corresponding dielectric constant will be epsilon r infinity will be equal to 1 plus P infinity star divided by epsilon naught E star, okay. So, this is the high frequency part. So, this also star, and at frequencies between 10 to the power 2 to 10 to the power 11 hertz, which is now lower than this frequency because this frequency is bigger than 10 to the power 11 hertz. So, lower than this frequency we have another contribution which we call as static dielectric constant, which is epsilon r s star. So, epsilon r s star can be written as 1 plus P s star plus P infinity star divided by epsilon naught E star. This is the saturation polarization that you are going to obtain after the dipolar polarization saturates, and this is the contribution from higher frequency, which is from ionic and electronic polarization. So, if you now replace the value of P infinity star here, you will obtain, so replacing this value here P infinity star. So, P infinity star will be epsilon r infinity minus 1 into epsilon naught E, okay. So, if you replace P infinity star, we will get epsilon r s star minus 1 will be equal to, so if I just simplify it, you do not need to write complete form. So, you will obtain epsilon r s star minus epsilon r infinity star, this will be equal to into epsilon naught E star, this will be equal to P s star. So, basically the saturation polarization that you will obtain because of saturation or dipolar polarization is nothing but the difference between the high static dielectric constant and high frequency dielectric constant. So, basically delta epsilon multiplied by epsilon naught E. This is what, and this is expected, right. This is what is the dipolar contribution that you get. So, this is the saturation you get. So, you can now modify the above expression as tau into, sorry, there is one mistake we have made, that is this will be tau, because 1 over f was equal to 1 over 2 f was equal to tau. So, this modification we have to sort of so this will be equal to tau, this will be equal to tau. My apologies for this correction. So, this is tau into d of Pd star by dt plus Pd star t, this will be equal to epsilon Rs star minus epsilon R infinity star into epsilon naught E star, right, because this was equal to, as I said, was equal to Ps star, right. So, this is the term that we get for Ps. So, assuming now we know that E star has a relation which is E naught into exponential of I omega t. So, since field is varying sinusoidally, it has a time dependence, we might expect the solution of P is also time dependent, right. So, we can write a solution. So, let us say we say that Pd star can be written in the form epsilon naught epsilon R star E star plus epsilon Rs exponential of minus beta t. It has some sort of form which is like this, and we want to determine here what beta is. Okay. So, if beta is like this, what we do is that first, if we say that this is the solution, we differentiate this dp, d with respect to t, and what we obtain is basically epsilon naught epsilon R star, and if you differentiate E, you will get I omega into E star, right, minus of beta epsilon Rs exponential of minus beta t. So, if you now substitute this in the above expression, in the expression that is shown above, so this is, the first thing is tau into epsilon or naught epsilon R star into I omega E star minus beta epsilon Rs exponential of minus beta t, then the expression for Pd, which is epsilon naught epsilon R star into E star plus epsilon R exponential of minus beta t. This is equal to epsilon Rs minus epsilon R infinity epsilon naught E star. Okay. Now, what we get is we can separate the frequency dependent part and non-frequency dependent part on two sides. So, this part will become minus tau beta epsilon Rs plus epsilon Rs into, so this is exponential minus beta t term, and the other terms can be replaced, can be written as, so this is slight rearrangement of the okay. So, both, now since these two sides are equal to each other, they must be equal to some constant, and it turns out that constant is equal to 0. So, basically we make first for the real part, so real part minus tau beta epsilon Rs plus epsilon Rs into exponential of minus beta t, this is equal to 0. So, from this one can see that beta is equal to 1 over tau. Okay. This is the first thing that we get, and now we do the same thing for imaginary part. So, basically we have made them equal to 0. Okay. And imaginary part, if we do the same thing, then epsilon Rs minus epsilon R infinity into epsilon naught into E star minus of tau epsilon naught epsilon R star I omega E star minus of epsilon naught epsilon R star E star is equal to 0. Okay. So, basically if you say that if Pd star is equal to epsilon naught epsilon R star into E star, then we can write. So, what it means is that Pd star minus this is equal to 0. Okay. So, if you do this substitution, what we will get is tau into I omega into PD star plus PD star is equal to epsilon Rs minus epsilon R infinity into epsilon R into E star. Okay. So, PD star becomes epsilon Rs minus epsilon R infinity into epsilon naught into E star divided by 1 plus I omega tau. Now, if you recall, polarization we had initially defined as D is equal to epsilon naught epsilon R into E, right, and epsilon naught E plus P, and this was equal to epsilon naught epsilon R E minus epsilon naught E is equal to P. So, this was equal to epsilon naught epsilon R minus 1 into E, which is P. If you look at this expression, it is fairly similar. Essentially, earlier we took dielectric constant, dielectric displacement after inserting a dielectric minus the dielectric displacement without the dielectric, that was equal to polarization, induced polarization. Here also it is the same. PD star is the static dielectric constant minus the high frequency dielectric constant multiplied by epsilon naught E, which is this term. Okay. So, here we are taking macroscopic values, maximum dielectric constant minus 1. 1 was when we did not have a dielectric, epsilon R was the one when you had dielectric. Here we are comparing two relative values. One is the high frequency contribution, another is the low frequency or nearly zero frequency contribution. Difference between the two is the dipolar part. So, here we are now looking at not looking at the total polarization, we are only looking at the dipolar contribution. Additionally, what we have in denominator is a term which is the frequency dependent term. So, if you make omega to be equal to 0, this becomes basically 1, alright. So, it becomes similar to what we have seen earlier. So, there is nothing too magical here, it is just that now we have done frequency dependent analysis. Now, if we combine real and imaginary part, what we get is PD star to be equal to epsilon R infinity into exponential of minus T over tau, okay, plus epsilon R S minus epsilon R infinity divided by 1 over I omega tau into, okay, this is what we get. This is the frequency independent term, this is the DC term, basically we can say time dependent DC term. So, time dependent decay of, let us say, because it is exponential minus T over tau. So, how does the DC contribution decays as a function of time? So, time dependent decay of nearly DC term. I mean, you can't say it is particularly DC because you have epsilon R infinity, there is a frequency dependence there, but it is at very high frequencies. For all practical purposes, you can consider this to be frequency independent. So, time dependent decay of the independent term, and then we have this another term which is basically the AC behavior at low frequencies, right. So, low frequency. So, this is basically the low frequency, this is ultra high frequency, which is nearly a constant term, how it decays with the polarization. So, essentially this contribution is going to be extremely small to dipolar polarization, and that is why most of the times we ignore that part. Now, considering the electronic and ionic polarizations to be frequency independent, okay, one can write. So, we have gone little over 30 minutes, but let us finish this part today. So, assuming that ionic electronic contributions as frequency independent, right, independent, we can write this epsilon R star minus epsilon infinity to be equal to PD star divided by epsilon naught into E star, right. So, what we have done is we have just taken the frequency independent of polarization. So, this becomes equal to essentially epsilon r star minus epsilon infinity. This is equal to epsilon r s minus epsilon r infinity divided by 1 over I omega tau into epsilon naught E star, and this at the bottom we will also have epsilon naught. These will cancel each other. What we will have is essentially epsilon r star will equal to epsilon infinity, sorry, this is epsilon r infinity plus epsilon rs minus epsilon r infinity divided by 1 plus I omega tau. And we know that epsilon r star can be written as epsilon r prime minus I epsilon r double prime. So, if you separate the real and imaginary part, what we will get is epsilon r double prime will be equal to epsilon rs minus epsilon r infinity into omega tau divided by 1 plus omega square tau square, and epsilon r prime will be equal to epsilon r infinity plus epsilon rs minus epsilon r infinity divided by 1 plus omega square tau square, and tan delta will be equal to correspondingly epsilon r double prime divided by epsilon r prime. This will be equal to epsilon rs minus epsilon r infinity divide into omega tau divided by epsilon rs plus epsilon r infinity into omega square tau square. So, this is what is the analysis that we have done, and these equations are called as Debye equations. Okay. So, these are called as Debye equations, and when you plot this dielectric constant as a function of frequency now, so epsilon r prime, let us say first, so there is a frequency, so let us say we plot log omega tau. So, at a value of omega tau equal to 1, you have a resonance that is occurring. So, this goes from epsilon rs prime to epsilon r infinity prime, right, and this is epsilon r double prime, it undergoes a maximum. Okay. And the tan delta maxima is, so this is for epsilon r double prime, the tan delta maxima is shifted to slightly higher frequencies. So, for tan delta you can plot the maxima like this, and this occurs at omega is equal to epsilon rs prime divided by epsilon r infinity prime to the power half divided by tau. So, you can find out that easily, the maxima at which point. So, this is what dielectric relaxation is. There is no resonance, there is a gradual change in low frequency dielectric constant, that is static dielectric constant, to high frequency dielectric constant at a frequency at which omega tau is equal to 1. So, this is also critical frequency. So, this is omega tau is equal to 1 at this point, and at the same point we have a maxima in the imaginary dielectric constant. Correspondingly, tan delta also shows a maxima at this frequency, which is close to the peak of tan. So, this is what is the dielectric relaxation, which is basically about slow change of dipolar polarization as a function of time. So, as a result we do not see a resonance, we see a relaxation of dielectric constant to smaller values as a function of time. So, we will stop here, we will discuss this further in the next class, and I hope that this has given you sufficient insight into how dipolar polarization is estimated as a function of time. Thank you.